In this day and age, information is practically all around us. Everything and nothing can be informationed. Information theory is a field that studies the coding and transmission of information. It was proposed by Claude Shannon in 1948 to seek the fundamental limits of signal processing and communication operations such as data transmission. One of the most important measures in information theory is entropy. Shannon classical entropy is described as the measure of uncertainty for the next outcomes or the measure of informativeness of a set of data. It is found that the higher the predictability, the smaller the value of entropy. Data with high predictability can be compressed into a smaller entropy measure according to Shannon's source coding theorem. Quantum information utilizes qubits, which can be the superposition of zeros and ones instead of bits. The quantum Von-Neumann entropy is a function of its density matrix and is given by the formula that if the quantum states are orthogonal, it will just simplify to Shannon's. Quantum algorithms and simulations could potentially give significant speed-up as compared to its classical counterpart, although that's not always the case. While quantum information is booming, the technological advancement needed to reach practical solutions might need to take some time. It is then interesting to see whether there is a region in between quantum and classical that could be utilized for algorithms or simulations, and if there is, what is its properties? In this project, we're interested in studying the quantum to classical transition through the notion of its entropy by using the formalism of quantum stochastic walk. Quantum stochastic walk is chosen because of its ability that allows the transition from quantum walk to classical walk by varying its decoherence parameter omega. The probability distribution of the walker is then obtained for various omega values. The density matrix visualization shows that as omega increases to 1, the off-diagonal term, which represents the coherence properties of the system, starts to disappear. At omega 0.03, an optimal top-hat-like uniform distribution is obtained, which could be useful for uniform sampling. Entropy analysis is done under the probability distribution, and the entropy values for Shannon, Ranyai, and Von-Neumann entropy are calculated. The Von-Neumann entropy is lower compared to its classical counterpart at the early intermediate range of omega ranging from 0.01 to 0.2. Lower entropy values could potentially be utilized in data compression. We also plotted the Von-Neumann entropy over time, which shows the entropy grows logarithmically and more rapidly as omega increases. Perhaps the maximum entropy in this early intermediate region could prove of essential use for some real-world applications that could be benefited from larger spread of network exploitation. We're also interested in the energy transfer dynamic of the FMO complex, which is a light harvesting photosynthetic protein complex. This has been discussed in many previous work with conflicting results regarding the supposedly long-lived quantum coherence. This energy transfer process happens at a remarkably great efficiency, which is peculiar since cis bacteriochlorophylls chromophores are technically in an environmental bath of protein, which is greatly fluctuating, and the process usually happens at room temperature. This indicates that there might be some sort of phase coherence phenomenon happening during this process, where classical computation had only proved a much lesser efficiency in the transfer dynamics. The size population against time are plotted for various omega. At omega 0, the erratic oscillatory behavior can be accounted due to the factor of low temperature or the factor of the non-existence of the protein bath surrounding the FMO complex. The protein bath controls the relaxation of the propagation of excitations in the FMO complex. Without this bath, the FMO complex acts as a purely quantum system, which would render it time independent and thus not functioning as naturally as it does. The size population versus time for varying initial excitations is also plotted. This recurring oscillation despite various initial excitation shows that coherent and incoherent dynamics exist in the FMO complex. This intrinsic dephasing factor in the energy transport could prove that perhaps a slightly dephased system could be of use in real-world problems. As is the trend in this research project, perhaps the middle ground between purely coherent and incoherent dynamics could provide an optimal way for algorithm design or physical processor simulation. Quantum stochastic walk as a formalism provide an interesting ability to model the intermediate region as quantum walk decoheres into a classical walk. This opens up a whole new door of exciting possibilities where the behavior of a system or an algorithm could be observed in this intermediate region. New studies and research are needed to study the characteristics and properties of this intermediate region, which could be utilized for potential future use in designing algorithms or simulating physical processes. Thank you.